All right. So this one is a little more complicated. And so we're on a roller coaster. And let's suppose that we're talking about somebody who has a mass of 80 kilograms. Um, and it's got some loop-the-loops in it. And at one point, it's traveling along, and the car with the person is going 30 meters per second. And what we want to do is we want to know, well, what's the normal force acting on the rider at that particular point? Okay, so we have to know what is that point and some stuff like that. So let me zoom in here just like this. So if we have 50 degrees there, then we can kind of imagine this thing is on a slope, and that slope is also 50 degrees. Okay, just like that. So you can sort of imagine if this thing went down to zero, that's like this thing going down to zero here. Okay, so you can work out that geometry if you're not real clear what's going on with all of that. If we look at our forces that we have acting, then we're going to have a normal force up here, and we're going to have the weight down here. And remember, we can split that weight into a perpendicular component and a normal component, or a parallel component there. Perpendicular and parallel components. So if we make our free body diagram, all right, when we're on a slope, it's usually really helpful to go ahead and make that free body diagram on the slope. And so we'll have our normal force here. And then here's where I'm going to put the perpendicular component of the weight. Here's where I'm going to put the parallel component of the weight. And there's the normal force, just like that, okay? So we're looking for the normal force. So let's go ahead then and jump right to Newton's laws. And so we're going to have here, and so let me call this the perpendicular bit. And so here I'm going to have MA perpendicular. So I've got the normal minus the perpendicular component of the weight. Now, is that equal to zero or not? Well, that depends if there's any acceleration. And in this particular case, since it's moving in a circle, there actually is some acceleration up this way. So there's my centripetal acceleration there. So I have to put MAC, and that's going to be mv squared over r. Since we know the speed of it, okay, so it's moving around a turn just like that, which means then that my normal force is going to be mv squared over r plus mg cosine theta, okay, where, of course, mg cosine theta is my perpendicular part right there, okay? So if you need to go back and review about objects on an incline and how we split those up with parallel and perpendicular, probably a good idea to go ahead and do that. Okay, so I'm going to hold off on plugging in numbers. I'm going to do some more algebra here. Let's call this v squared over r plus g cosine theta. All right, now I feel like we could probably put some numbers in there. So we're going to have 80 kilograms and 30 meters per second quantity squared divided by a radius of 15 meters. And that's 9.81 meters per second squared onto cosine of 50 degrees. Okay. Now, when you run those numbers, what you're going to end up with is 5304 newtons. Okay. Which again, I've not done a very good job with my numbers here. I really blew it with the ice skating one, and this one's pretty extreme too. In fact, that number right there turns out to be 6.8 times the weight of the person. Okay, so again, probably be a lot of fun, unless you're older or I don't know, but I'd wager a good percentage of people on that would probably pass out right there. They just clock right out. Anyway, so that's the normal force. Now there is another part to this, which it says what's the net force. Okay, so this means the total force that's acting. Okay, the total force that's acting. All right. So let's come back here. Okay, and realize that we're out of balance in this direction. So that means we've also got some acceleration this way. So let me call that A parallel. Okay, we've got some acceleration down that way. So this thing is trying to speed up. So it's accelerating on a tangent to its path, plus it's accelerating perpendicular to its path. That's the centripetal acceleration. Okay. So let's set that up. Use a different color here. And I'm going to set that up like this. Here. Okay. And let's call that the parallel bit. So we're looking for the parallel acceleration, which is just going to be the parallel component of the weight is MA parallel. This is mg sine theta. It's MA parallel. My m's cancel, and my acceleration there is just going to be g sine theta. So if we put in some numbers, 9.81 meters per second squared, sine 50 degrees. So the parallel component of our weight is 7.51 meters per second squared. Okay, so that's pretty impressive. Now, we didn't actually ever calculate what the actual centripetal acceleration is. So let's do that while we're at it here. Okay, which means I need this part right here. That's our centripetal acceleration right there, v squared over r. So v squared over r, 30 squared over 15, and that I forgot to calculate. So let me do that here. Boom. So 30 squared divided by 15. Here we go. 16? 60? Whoa. Holy crap. Okay. I didn't do a great job of making realistic problems today. Okay, there we go. Just like that. All right. So now I've got this guy, the centripetal acceleration, and which is also my perpendicular component. All right. So those are the same thing in this particular case. All right. All right. We're interested in that because if we're going to get the net force, all right, if we're going to get this guy up here, then the easiest way to do it is actually to say that the total net force is MA, where A is the net acceleration. Okay. So what we'll do is we're going to say this is M, A parallel squared plus A perpendicular squared, like so. And so we're just using Pythagorean's theorem. We've got these perpendicular components for acceleration. All right, so then if we put in our numbers, we've got 80 onto the parallel bit, which was 7.51. And then the perpendicular bit, which was enormous. Okay. And we're going to get rather a large net force on this. So we get 48.37 is the net force acting on my person there. Okay. And again, probably not safe. Actually, this roller coaster is not going to pass inspection. Okay. All right. So we've got one more to do. All right. That'll be the Nascar problem. Okay. And it's going to combine elements of all these things that we've done so far.